All right, so we're going back to information flow security again. So our fourth talk is given by Shamiek Mangipudi, and he'll be talking about generalized policy-based non-interference for efficient confidentiality preservation.
Hi everyone, I'm Shamiek and this is joint work with Pavel, Patrick, Malte and Savvas. Welcome to the talk on a generalized policy-based non-interference for efficient confidentiality preservation. So data has become the new currency with the rise of information-driven economies and the demand for smarter apps that have intense computational and scalability requirements has driven the need for large-scale data processing in cloud resources. Foundational models and, among others, are a case in point. However, the cloud comes with its own concern of multi-tenancy, where the confidentiality of the data is at risk. As an example, the background here shows the number of user accounts compromised due to data leaks in different organizations. So some of the approaches to deal with these risks are the download and compute approach, where the cloud is primarily used as a storage device, and this causes underutilization of cloud resources, and software-based techniques such as homomorphic encryption and others have performance overhead. And we also have trusted platforms that provide very specific guarantees in cloud infrastructures, but these are not uniformly available. So we propose our solution, Hydra, which is a mechanism-independent hybrid approach to preserve confidentiality of data in the cloud. And this is the architecture of our approach, where a data analyst submits a query, and that is submitted to the cloud, which has a set of trusted resources and untrusted resources, and the computation is carried out, and eventually the result is returned back to the data analyst. As we can see, this approach has a lot of components, different security guarantees and threat models are involved. So it is hard to reason about end-to-end security in this setting. And shortly we'll see that we use a language-based approach to deal with this. So what does Hydra have? Hydra uses a combination of hardware and software-based security mechanisms. Software-based mechanisms include partial homomorphic encryption, such as AES-DET and LGAMAL that support different operations. And we also make use of trusted execution environments such as Intel SGX, and also trusted client-side computation to overcome limitations of PHE. And we adopt this language-based approach because it is based on classical security principles, and it is also equipped with a tractable method to establish the desired security properties that we want to guarantee. So we'll look at the threat model which Hydra protects against. So we only consider honest but curious adversaries that can see the data but cannot modify it. And we represent each adversary as a downward closed set of domain and scheme tuples, where domain is representative of hardware-based mechanism, and schemes are representative of software-based mechanisms. And we denote all the set of adversaries by this cursive A. And we also assume that the adversary can only observe the final result of the computation. And here is an example of the lattice that we use to label different security requirements. And this is our novel security policy on the right. So mathematically, our security policy is a mapping from labels to a set of domain and scheme tuples. And we assume that every label L provides sufficient confidentiality guarantees required for that level. Intuitively, a DS tuple mapped to a level means that data labeled with L, when present in domain D under encryption scheme S, satisfies the confidentiality guarantees. As an example, we have SGX with no encryption as part of, this is mapped to the label high. So it is safe to keep a data which is labeled high under no encryption scheme inside SGX. And the connection to adversaries is that if the intersection between the adversary and the DS tuples that this label maps is null set, then the adversary cannot tamper with the data. And moving on to the model of secure programs that we use to represent. So our language is based on lambda calculus, and we use this to have an easy integration into data analytics frameworks like Spark that make use of Scala. And we also have provable properties like progress and subject reduction. We'll quickly go over the syntax of Hydra with a focus on security and the relational aspects that we target. So firstly, we have a set of labels that we just saw in the previous slide. And then we have a set of schemes and a set of secure domains, which represent the software and hardware-based security mechanisms. And then we have relational operators like filter, project. And then we have relational tables, we have rows, potentially encrypted constants. And then we have a lambda function with an annotation which tells in which domain the function should be executed. And finally, we have expressions, which are like table name, and then we have query operators, and we have encryption and decryption primitives, and we also have a return type, which annotates the domain in which the expression is present. And finally, we have types. We have the function type, and the standard record type, and the relation type. And it's interesting to see that all of these are annotated with schemes and labels. And the blue stuff, which is highlighted in the syntax, is it is supplied with some defaults when the data analyst submits the query. And these defaults are transformed by our transformer to emit a secure version of the query. Excuse me. And the green annotations are only present at runtime. So what do we want to ensure with this secure model? We target the non-interference property, which is a classical information flow policy. And this ensures the independence of confidential and public information. In essence, as we change secret information, that does not leak into public information. That's the core idea. And here is a a picture which shows that. So we have taken the classical non-interference property and augmented it with our novel security policy to formulate a new security property called S non-interference, or SNI for short. And we also define the notions of secret and public for inputs based on the intersection of the adversary set A along with the domain scheme tuples that a given label is mapped to. So for example, if an adversary cannot break any of the DS tuples mapped from a given label, then that information is deemed secret. And on the flip side, for the outputs, if the DS tuple is not present in the adversary set, then it is unobservable by the adversary. And we also define equivalence relations in order to define the idea of unchanged with respect to an adversary. So we have two sets of equivalence relations, one for input and one for outputs. Essentially, the equivalence relation for inputs says that it says that inputs are only allowed to vary in the parts that have label L. And for the output relation, we say that outputs can only vary in the parts that have that are protected by label L. And this ensures that an adversary who does not have access to any of the DS tuples that a given label maps to cannot observe the outputs. And this is a snippet of our equivalence relations. The first two rules deal with the inputs and outputs, which essentially say only parts labeled with L can vary for the input case, and for the outputs case, only parts labeled with L are safe from the adversary. And the other two rules on the first row say that equal values are equivalent, and all the rules on the second row say that these rules are supplied, these rules are transferred through the structure of the types. And we use equivalence relations and all the ingredients seen till now to ensure end-to-end confidentiality guarantees using typing rules. So we have a security type system that enforces SNI through compile time type checking. Here is a snippet of some of the rules. So the first rule says that an operator expression is well-typed if the operator itself is well-typed and all the labels, the resulting labels of the computation are a lattice join of all the labels of the input arguments. And we also check that if any of the input arguments are encrypted, then all of them are the same encryption scheme. And the second and the third rule, decryption and encryption, deal with checking compatibility requirements of schemes and labels along with the domain in which the operations are happening. So for instance, the decryption rule checks that the value being decrypted is compatible with the domain in which the decryption happens. And so this brings us to the main theorem of our work, which states that if an expression is well-typed or a program is well-typed, then it enjoys the S non-interference property. And please read our paper for more details on the formalism. And the way in which we prove S non-interference is by extending the original language with bracketed expressions and simulating two executions of a program using the bracketed expression. And that essentially boils down to showing the subject reduction proof for the extended language. And we quickly look at the workflow of Hydra, where a data analyst submits a Spark SQL query, and that is transformed using the security policy annotated data schema and a heuristic to emit an annotated query that has all the security annotations in place, and this query is also type checked. And then this is passed through a compiler and optimizer to produce a final execution plan that has different components executing in various security mechanisms. And this execution plan is submitted to the cloud, and which has a bunch of security mechanisms, and then the result is eventually returned. We have evaluated a prototype implementation of Hydra on AWS cluster, where we run Hydra in 3 modes corresponding to the heuristics that we saw earlier. And our approach is competent with state-of-the-art systems, providing significant speed-ups, and also it is fast with respect to its own heuristics. So that brings us to an end of this presentation, where we present a system that employs this extensible set of hardware and software mechanisms, and we also protect data in use as opposed to protecting data at rest and in transit, and we have formally proved our security guarantees. Thank you for your attention, and I'll be happy to take some questions.
Questions? All right, I'll start with one. So here there's a policy component, right? We have to know how to annotate my program so that things can be protected properly. In your system, how much of the overhead that the programmer has to deal with policies?
So we offload the policy declaration to a security expert, which is basically the mapping between labels and domain scheme tuples. And our transformer takes in this security policy and automatically emits the annotated security-aware query. So it is not a lot of load for the programmer, because we initialize these annotations with some defaults, and then the transformer eventually fills in the right values for labels and domains and schemes.
So for the mapping, it's one mapping per application, per hardware setting, or you have one mapping for all? Like how many mappings you have to write for your application?
So it is one mapping for a specific set of hardware and software security mechanisms. And that can be reused as long as the security infrastructure is not changed.
Anybody got questions? So now here you enforce strict non-interference. What about if I want to have some amount of declassification? How would you deal with that in your system? Yeah,
that's a good question. So we do not have the need to tackle declassification, because we have this escape hatch mechanism of falling back onto a trusted client side if there is no way to run the query on the cloud. So we don't explicitly have to support declassification.
Questions? Maybe I'll do one last question. So it seemed to be interesting work. If I want to extend to more hardware, what's next for you? Like, is extending to more hardware, it's easy for you, therefore it's not a challenge anymore? Like, what are the additional steps for this project?
Yeah, so we are extending with various other symmetric homomorphic encryption schemes and secure hardware mechanisms. So that will mean we add more red boxes here. I'll just show you. The pink boxes on the top. Mm-hmm. So that is, they are secure implementations of these mechanisms. So we provide more backend code and make sure that it is invoked appropriately when we add a new security mechanism. So the primitives add on, and we have to add some components to our syntax, and the typing rules would essentially be the same as long as we don't change the labels.
Yeah, makes sense. I thank speaker again. So.